Hello AP Chemistry and welcome to 19.6, where we talk about this table from your guys' book and how to qualitatively assess or how to qualitatively use the delta G equals delta H minus T delta S equation, right? So a lot of questions, right, that we answer are math-based, right, where if I know the value of delta H and I know the value of delta S, right, I can plug that all in and calculate delta G or whatever two pieces and calculate the third, right? But there are also a lot of questions that require you to be able to think through a set of observations and decide what the last one must be with no numbers, right? Because that's where the demonstration of understanding comes in, right? Whereas a lot of people can just based on like patterns, I'll just plug it in and do some math, right? Whereas in order to qualitatively assess if something the sign of something, right? You hypothetically you have to understand it a little bit, right? Unless you've memorized every scenario, which is, I guess possible also. But anyway, the point is it's supposed to test that you understand what you're talking about. So first, we have that equation, right? So you got to know this, okay? Because that's the relationship, right? And don't forget that delta S is tied to the temperature because temperature has such a huge effect on delta S, right? Because obviously as temperature changes, right, delta S changes, right? And we've seen that, right? Things to think about, right? So delta H, right, again, is enthalpy, and that's an exchange of thermal energy, right? So observationally, right, so if we're looking at a scenario or evaluating some information, right, what we're looking for here is a change in temperature, right? That's what's going to give us clues about delta H, right? If the temperature of the surroundings goes up, that's because the process is exothermic, right, and has released heat to the surroundings, right? If the temperature of the surroundings goes down, right, that's because the process absorbed heat from the surroundings, right, and is an endothermic process, right? So we can evaluate delta H based on observations about temperature, okay? Delta S, there's not so much an observational thing there, right, because there's, no, it's not something we can just like measure with a thermometer, right? But delta S, we can do all that same analysis we did before, right? Like moles of gas, right? Would be the primary way to go, right? Or just motion in general, right? And don't forget that all of this is about a process, right? So most often we are talking about some reactant and some product, right? So you're never, reiterate, never going to write an answer where you can just deduce the sign of delta H by saying bonds are broken, right? Because for every reaction where we have reactant forms product, right, there are always bonds broken on this side, right? Always, right? That's how that works. And always, as well, there are bonds formed on this side, yes, right? Which means that you can't just think about, oh, it's a decomposition, so it must be endothermic, right? Not necessarily, right? Because there are bonds broken on one side and always bonds formed on the flip side, and it's the balance of the energy for both of those that determines whether or not the overall enthalpy is positive or negative, right? So you will never ever try to use something like that as a justification, right? The justification for your enthalpy is going to come from the temperature, right? And there are some things that's just expected you know, right? Like combustion, yep, that's an exothermic process, and it's expected that you know that, right? Okay, other than that, and then obviously state changes, you should know that solid to liquid, right, is endo, liquid to gas is endo, and then the reverses are exo, right? Okay. All right, so then analyzing the table and thinking through that, right, we have this scenario where a process is spontaneous at all temperatures if delta H and delta S are both favorable, right? Favorable meaning energy is released, thermal energy is released, so it's exo, right? This is exo. And it's got a positive delta S, meaning its entropy is increasing. It has more microstates than it did before, right? And then what that means is in that scenario, if both H and S are favorable, then my process, whatever it is thermodynamically favorable at all temperatures. Yes? Thermodynamically favorable at all temperatures. In a different scenario, right? If we have something that is positive, delta H, so it means it's endo, and it has a decrease in entropy, which means, so endo means energy has to be put into it, right? Negative entropy means it has fewer microstates than it started with, right? That is going to be not thermodynamically favorable at all temperatures. Yes, does that make sense, right? So what that means, right, so if we look at that a red scenario that says XO positive delta S negative at all temperatures, that means that when we look at this equation, there is no value of T such that delta G would be positive, yes? There is no value of T that would make delta G be positive, yes? Does that make sense, right? And another way to think about that is sort of evaluating what the absolute values of my T delta S versus my H, right? What those values are, right? Does that make sense? Okay. Likewise for the green scenario, right, where if we have endo and a negative delta S, right, there is no value of T that could make a delta G be negative, right? Does that make sense? Okay. And then we get into our last two scenarios that require ever so slightly more thought. Okay, so let's look at the first one. The first one says that we have XO, right? And this one, though, right? Negative entropy, meaning we have fewer microstates on the product side, right? Is going to be temperature-based, right? Whether it is positive or negative is going to be temperature-based. Yes, does that make sense, right? So we have this reaction or equation that says delta G equals delta H minus T delta S, right? And if we think in this scenario, if this value is negative, right, and this value is negative, and again, the T's are always positive, so that's not really a factor. What that means, right, is that we are essentially adding the T delta S value, yes? In this scenario, we are adding, because that's what happens when we flip it, right? Adding T delta S, right? That's what math says, right? So then, what that means is that as long as the value of T delta S is less than the value of delta H, absolute value, right? As long as the value of T delta S, absolute value, is less than the absolute value of delta H, then delta G will be negative, right? Which is why this is spontaneous at low temperatures, yes? Okay. And then we have that other scenario, right, which says that if we have something that is endo, but there is a favorable delta S, meaning that it has more microstates at the end, right? It is spontaneous, also based on temperature, but in the opposite way, right? And so let's do the equation first. So delta G equals delta H minus T delta S, right? And this one is positive now. This one is positive now, and there's a minus sign in the middle, right? So in this case, if we're looking at absolute values again, although I guess since they're all positive, it doesn't really matter, right? So when eventually this T delta S value is larger, or when the magnitude of T delta S is larger than the magnitude of delta H, we can get a negative delta G, which means that when high temp happens, right, we get a negative delta G, right? Whereas in this one, when a low temp happens, we have a negative delta G, okay? And so if we look at these scenarios, right, so these first two, right, we have both terms either favorable or unfavorable. So then temperature has no impact, right? Then we have the last two scenarios where one term is favorable and one term is not, which is why temperature then becomes a factor there. Yes? Okay. So some follow-up questions at the bottom. So if a process is thermodynamically favorable, which means negative delta G, okay, and endo, which means positive delta H, right? What can you conclude about delta S, right? Well, in order for delta G to be negative, if delta H is positive, that means S must be, right, must be a positive delta S, right? Because that's the only scenario where a positive delta H could produce a negative delta G, yes? Follow up, if a process is thermodynamically favorable, negative delta G, and decreases in entropy, so negative delta S, what can you conclude about delta H? Well, the only scenario where that's possible, right, is if we also have a negative delta H, right? Does that make sense? Like, so qualitatively we can, so in these two, right, we started with H and S and reasoned about temperature and G. Down here, if we have a G and one thing, we can reason about the last one, right? Does it make sense? Think about it. Really, all this is just a qualitative discussion about the math at hand, right? Make sure it makes sense. We'll talk about it some more in class. And if it doesn't, see me soon. All right. Thank you for listening. Be good, and I will see you soon. Bye.